Hello, my name is John Ratzlaff. This is for FTT 122 at SDI. I'm going to be going over a few things today. First, I would like to start with trajectory and sights. So, trajectory refers to the path of a projectile which follows under the influence of forces like gravity and air resistance. Sights are an aiming device in a firearm that help align the shooter's line of sight with the intended trajectory. Really quick, so if we're going to be, let's say, aiming at this brush here, and then this is going to be our barrel, so we want to aim right here between the color differences. So the line of sight is going to be that direct line of sight that you use either with like iron sights or a scope. That's going to be your direct line of sight. So, and aiming too, you're going to be able to, you have a few different ways you can put like your aiming aperture device if you have something together. So let's just use iron sights for that. So you're going to follow that front iron sight post, whether it goes up or down. That's going to be your aiming piece. But the biggest thing that I just want to portray for you is that you have your line of sight with the sights you use, but then you're going to have the trajectory of the bullet. So depending on your distance, your line of sight is still going to be the same, but that trajectory that round is actually going to take, it does make an arch-like movement for that actual point of impact. And that's going to be the difference in your line of sight versus your actual trajectory of that bullet coming in to make that impact. Um, Gyroscopic drift, so also known as spin drift, gyroscopic drift occurs when a spinning bullet experiences a slight sideways deviation due to its spin interacting with atmospheric conditions, or actually the aerodynamic forces. So we're going to use the spray can. So a perfect without spin drift, you're going to have a round that's just going to go straight, and you're really going to see the spin drift over a prolonged distance when shooting. But because that round is spinning, you're actually going to have that deviate, like on a right hand twist rifle, up and to the right. So that spin is taking it up and to the right instead of just going straight. So drag, a really good way to describe drag in of itself is that's the aerodynamic resistance a projectile encounters as it moves through the air, slowing it down. So if we have something like let's just take this like hockey puck, and then we have this piece of paper, this cardboard. So if we have it at the same distance, one thing that we're going to notice is that this is going to have a lot more drag than if I took this hockey puck and laid it down. It's going to have a whole lot of less drag. Actually, I'll just use a screwdriver for this example. So we're going to let both these go at the same spot. And what you're going to notice is that screwdriver goes down very much quicker, or a lot more quick. Gravity has that effect on it. And then that paper has so much more drag that it's actually slowed down in of itself. I want to go over the Magnus effect. So that Magnus effect describes the force exerted on a spinning object moving through the air, causing it to curve in its path. So the best way kind of to add that as well is, so it's kind of like if you throw like a curveball, regardless with a tennis ball, this is just what I have here is like a hockey puck, but you would throw that pitch going in, but then you would add curve to that. And that's going to just demonstrate that Magnus effect. So it would be coming in, it's a little bit different than spin drift, but that can actually deviate and go a specific direction depending on that spin in and of itself. The Coriolis effect and the Atovis effect. So we'll talk about this really quick. So referring to our SDI textbooks this week, the Coriolis effect impacts the projectile on a horizontal plane when shooting north or south, and then the Atovis effect is going to impact that projectile on the vertical plane when shooting east or west. So in the northern hemisphere, the deflection will always be to the right, regardless if you are shooting north or south to north, and the opposite is true of the southern hemisphere. The deflection in the southern hemisphere will always be to the left. That Atovis effect is it causes that deviation along the vertical plane of a projectile's trajectory, And because the Earth is round and spinning, when shooting east or west, that target is rising and falling. So that's one thing to always remember too. That Atobus effect is always going to be strongest at the equator and weakest at the poles. So with that being said, we're going to use this hockey puck as it's spinning. I want to think about the Earth spinning and rotating, and that Coriolis effect having its effect on that horizontal plane. So that's going to have the deviation from that horizontal plane, and that Coriolis effect is going to have it while it's spinning on that vertical plane. Kind of hard to explain, just because there's a lot of moving pieces to it. So hopefully you guys understand that a bit. Vertical angles. So vertical angles, another one that's kind of hard to explain kind of with everyday objects, but we'll get to that. Shooting at upward or downward angles affect the projectile due to the way that gravity influences its path. With aiming uphill or downhill, the actual distance gravity acts upon is shorter than the line of sight diameter to the target, leading to a higher point of impact than anticipated. I've always been told, just throughout my life and my shooting experiences, that if you're shooting at a downward angle or an upward angle, and you're aiming for a target's center mass, you do want to put that point of aim lower, maybe towards the waistline, and you'll have better luck with that. So the last one here I want to describe is going to be transonic ballistic performance. So transonic refers to the speed close to the speed of sound, where a projectile experiences changes in its aerodynamic forces, affecting stability and accuracy. So we'll use this pin again. So when a round is coming in and it's hasn't reached its transonic speed yet, it's on a correct flight course, ballistic coefficients and everything is measured. When it hits that transonic stage, instead of having that forward constant force momentum with it being non-subsonic, you're going to wind up having, when you hit that transonic range, that's when the bullet's going to start to be unstable, and it's going to start to do weird things because it doesn't have that same force at which it got to that point at. So that can lead to some accuracy discrepancies. Hopefully this is helpful. A little over on time, but hopefully I got my point across to you. Thanks much. Bye.